Hi, hello, welcome to my channel, Dr. VRK Reddy Mathematics. I am really thankful to the subscribers and viewers for your continuous support. Today, the channel is able to get 100 plus subscribers and close to 600 views. And the credit goes to all of you, those who supported me. And today, I would like to make a video on group theory, which covers up to subsets, subgroups, and further I'll try to cover few theorems on these topics, taking 2 or 3 hours to cover the possible topics in group theory, on subgroups also, homomorphism, if possible a few examples on isomorphism. Further, I will take you to the ring theory and field theory with few examples. That is the idea. So before I take you to the group theory, I would like to list a few applications of group theory. So group theory has a lot of applications in physics, chemistry, and computer science. Of course, this group theory's further techniques are used in solving Rubik's cube also. So especially if you look at computer science, this is actually precisely used in cryptography, where encryption and decryption depends upon the key. That key can be made stronger so that the hackers cannot crack the key. So that is another theory, but this will be used there, and I don't want to go more details in it. And especially physics and chemistry also, the structure of the compound can be analyzed and further based on its polarity, and then spectroscopy. This group theory is useful. Also, group theory is used some applications in harmonic analysis, combinatorics, and algebraic topology. With this introduction, I want to take you to the group theory. But I would like to make a point. Earlier, this channel handle was at its maths I take. Now that has been changed to a purpose. The change has been made to get more visibility in YouTube search. With that idea, the name has been changed. Please do subscribe if you like the videos, and also please don't forget to ask the topics, post it, comment it, and let me know. This is my 4th video in this series, so that it will helpful to the viewers. Thank you. Let me take you to the group theory. I would like to give a big credit to the Abel and Galois, who has developed this group theory in 19th century, and they have made very significant contributions. So before I will take you to the group theory, I hope you know that set theory. Set. Whenever there is a set, that is, set is represented by a capital letter S, and that is holding elements something like this, A, B, C, and so on. That is holding elements. So whenever you have a set, you can actually apply some properties over that and see whether it is satisfying certain conditions or not. For example, you want to define a relation on S. That is, whenever you pick two elements, x comma y belongs to S, how these x comma y are related with respect to the relation is matter. And you have to check few properties, like you say that whether it is reflexive, that is, x is related with x, reflexive. And then whenever x is related y and y is related to x is the question. then you say symmetric. And whenever x is related to y, y is related to z, and then can you conclude x is related with z, then you called transitive property. So any relation that is satisfying, you call it equivalence relation. Equivalence relation. If R satisfies all three, 1, 2, 3, 1, 2, 3, all three properties. So with this, that means you can see that whenever you are defining a relation, the elements of the form, the paired form, and you are trying to see that in which relation, how these elements are connected. So to define a group, we must have a set. So non-empty set, we must have a set. Have a non-empty set. A set Z, and where you are defining a operation as a function. Operation, call it binary operation. Binary operation, I represent it with star. Star can be any function. So I'm not saying that, I'm not defining it precisely what is this function. I will see that what is that map later. You are defining from G cross G to Z, and in such a way that A comma B, if you pick, goes to A star B. That is where for all A comma B belongs to Z. Whenever you take two elements in Z, that must, the pair actually, the relation we have seen that how these order pairs are there, that pair must satisfy this relation A star B. This is the relation I am defining. So with this relation, I have to check few properties, whether this relation is satisfying, whether the relation, or I mean especially it's better to, whether the operation operate, whether the binary operator satisfying certain properties. What are these properties? We can see that those properties are actually, the first one is closure. So we call it closure property or closure axiom or property. Second one is associative axiom or associative property. Third, you call it identity axiom, or you can say that identity property. You can call it, last one is inverse axiom, or inverse property. So any set with that binary operation satisfying, that is any set G with the binary operation, satisfying all these four properties. So we can say that all four properties we call G is a group group with respect to the operator star. So you can say that in other words G comma star. So is a group if it satisfies all four properties. So now we'll see some examples and then how to check them. So for example, if you want to verify how these four properties can be checked, first one is that you have to take for all a comma b comma c belongs to Z. So you are saying that a, b, c are three elements in G. Now, so for all a comma b belongs to Z implies a with respect to the operator a star b, because the star is the operator defined over G. I mean binary operator defined over G. Therefore, a star b must be in Z. That means whenever you take two elements and then apply the operator, the output must be in again G. In that case, we call it G is closed. If this is satisfied, G is closed. So implies G is closed with respect to star. So star is the operator, with respect to that it is closed. Second one is for all a comma b comma c belongs to Z implies a star b star c must be equal to a star b star c. So this is, so that means whenever this is satisfied, then you say G is associative with respect to star. That is another one. Now we are moving to property 3, that is for all E belongs to G, there must be an element E belongs to G where E is abstract, I mean some element, some abstract element need to be fixed. Need to be fixed. How that element can be fixed? With the property. What is that property? There exists a E in G such that A plus E or A star actually, sorry, A star E is equal to, A star E is equal to E star A is equal to A. That means you apply the binary operator A with other element. I mean this must be valid for all A, not for single element in A. It is valid for every element in G. Every element in G. So that means for all A, whatever element you pick in G, you apply star with respect to E, and E star, the element must be that element itself. In that case, you can say E is the identity element. So such that this case is, this condition is satisfied. Then we say E is the identity. Then we say E is the identity element. Then we say E is the identity element. In G. And next we have another property, that is inverse of an element. So therefore, how that inverse should exist? For all E belongs to Z, whatever the element you pick it in G, there exists a B. So that means for every element you pick in G, you can pick some elements A1, A2, A3 and so on. Whatever the element, there must be a B1, B2, B3 such that there must be a B belongs to G such that such that A star B is equal to B star A is equal to identity element. Whenever you are getting identity element, whenever you operate A over B with respect to the binary operator and B over A with respect to binary operator, you should get identity element. So that means you can say, that means B is the inverse of A. B is inverse of A, and this inverse should exist for every element in G, not for one element. Every element, this property must be valid. Then you can say G comma star is a group. So whenever a group is satisfying with these four properties, whenever a set with respect to the binary operator satisfying all these four properties, we call it is a group. Whenever something is a group, you can extend further as a commutative group. Next property is commutative group. This is it must be commutative group is a little extra. One more axiom it has to satisfy. What is that axiom? First of all, G comma star must be a group. In addition, for all A comma B belongs to G, A star B is equal to B star A. That means order of applying the operation, it doesn't matter. First you are applying over the first element and the output must be same. You apply, change the positions, you apply the binary operation. We have seen that A star B and B star A, already G is a group, therefore A star B is coming under closure, therefore B star A is also coming under closure. But if these two are same, especially you take matrix product, if you take, so AB need not to be BA all the time. Therefore, those there is a special case where you can see that commutative property is failing. Therefore, there are groups that are actually a group only, not a commutative group. So, to be a commutative group, it must satisfy this condition. This is an extra condition. Now, you may ask examples. So can you check n comma plus? N is the natural number set. Addition. So it is very easy. First, axiom 1, that is closure property. For all A comma B belongs to N, A plus B belongs to N. Addition of two natural numbers is a natural number. Therefore, it is closed. Therefore, N comma plus is closed. And axiom 2, that is associative property. What is that? For all A comma B comma C belongs to, for all A comma B comma C belongs to N, you can easily show that B plus C, because whatever is the order of addition, you pick any numbers, you add first two numbers and add that resultant one to the third number, it must be equal to, first add third and second element and then add it to the first natural number. The order, this output is same. Therefore, N comma plus is associative. Next, identity element, axiom 3. Identity element, identity property or identity element. Whether is there an element in N such that is for all a belongs to n, is there a e such that how this e must satisfy some condition, that is a plus e is equal to e plus a is equal to a. For example, if we take a plus e is equal to a, this gives you e is equal to 0, but 0 doesn't belongs to n. There is no such 0 in n. Therefore, n comma plus is not holding n is not holding 0. Therefore, this is not holding the identity property. Hence, we can say n comma plus is not a group. So you can deny it. You don't need to prove further whether it is satisfying inverse property or not. If you want to verify, you can verify the inverse property also. It is going to be failed. How do you show that? It is a plus b is equal to e, but e is not part of this n comma plus. Therefore, this is ruled out. Therefore, n comma plus is not. Suppose example 2, if you take example 2, n comma multiplication, that is n is again natural number set, this is operator is multiplication. That means you take product of any two natural numbers. First, closure as a comma b belongs to n for all a star a multiplication b belongs to n. You make any product of two natural numbers is again a natural number. Associative, this is also associative for all a b c belongs to n. It doesn't matter order, doesn't matter how you are producting the numbers. So this must be equal to a star b star c. Therefore, that is actually satisfying associative property. Next one is that identity. That is, for all e belongs to n, is there a number e such that a multiplication e is equal to e multiplication a is equal to a. Yes, that is possible. When e is equal to 1, a into 1 is equal to 1 into a is equal to a. Therefore, now you see that earlier n comma plus was not holding the property, identity property, because lacking of 0 with respect to addition. But now when you take with respect to multiplication, n comma multiplication is holding or having an identity element. So one more property we have moved further compared to n comma plus. And now inverse property. Now you are taking for all a belongs to n, is there a b belongs to n? So whenever a is changing, b also changing. Remember that. Is there a b? For every a, is there a b? For every element in a, is there a b belongs to n such that a multiplied with b is equal to b multiplied with a is equal to identity element e. But you know that identity element is 1. That means a into b is equal to 1 implies b is equal to 1 by a, but this doesn't belongs to n because natural number set is not holding fractions. Hence, you can conclude that n comma multiplication is not holding inverse elements for all a belongs to n. Only for one self inverse, 1 into 1 is equal to 1. 1 is the identity element, 1 into 1 is equal to 1. It is only the element that is holding the inverse. Rest of the elements, you pick 2, 3, 4, 5, 1 by 2, 1 by 3, 1 by 4. All these elements are not part of the natural number set. Therefore, you don't get any inverse. Hence, it is also failing to satisfy the group property. Now, let me take another example. Example is z comma plus. Z is set of integers. Set of integers. Set of integers. The moment when you pick set of integers, that is actually, we have seen that two properties, that is closure property we have seen from the natural number set, that is closure property for all e comma b belongs to z, a plus b belongs to z. That is true because sum of the two integers is again an integer. And second property is associative property. For all e comma b comma c belongs to z, you can say that e plus b plus c must be equal to a plus b plus c. So addition of integers, it doesn't matter in which order you are adding, whether you are adding a plus b or c plus b or whatever it is still holding, it is actually satisfying the associative property. And third one is inverse, identity element. Third one is identity element. So in this, for all a belongs to z, there exists an element 0 such that is the identity element actually. A plus 0 is equal to 0 plus a is equal to a. It is valid for every, whatever the element you pick it. 0 is sufficient to act as a identity element. Therefore, you can say that 0 is the identity element. 0 is the identity element. 0 is the identity element. Last property is inverse element. That is, for all a belongs to z, is there a b belongs to z such that a plus b is equal to e is equal to, of course e is 0 in this case, b plus a, that is a plus b is equal to 0 is equal to b plus a. Suppose if a plus b is equal to 0, which implies b is equal to 0 minus a, that is minus a. So if you pick element a, there exists a minus a such that a plus of minus a is equal to 0. Therefore, for all, whatever the element, for all a belongs to z, this minus a is behaving like a inverse of the element. There exists minus a, of course I can say b such that b belongs to z such that a plus b is equal to 0 is equal to b plus a. Hence, z comma plus is a group. You may ask how the inverse exists. You pick any element a in z, a, b, c, d. A inverse is minus a, b inverse is minus b, c inverse is minus c. Suppose 5 inverse is minus 5, 10 inverse is minus 10, minus 5 inverse is plus 5. something like that, you are actually able to get to satisfy that condition. Now, if you want to see further whether it is satisfying commutative, now we will check whether it is satisfying commutative property or not. Commutative property. What is that commutative property? Whenever you take, for all a comma b belongs to z, a plus b is equal to b plus a, whether it is true or not is the question. Since the operation is addition and a comma b are the integers, then order doesn't matter, therefore you can simply add them. That gives you a plus b must be equal to b plus a. Therefore, for all a comma b belongs to z, hence you can say z comma plus is a commutative group, is a commutative group, or you can say that abelian group. You can also call it as an abelian group also. Okay. Now, so these are actually simple examples. I mean, if you want to pick something like a group, a set, something like this example. Another example is example. So we are taking a finite set. See, n, z, all these are having infinitely many elements. But now, if you take the 1 comma minus 1 comma I comma minus I, a finite set with operation, with multiplicative operator. Whether the set with respect to multiplication is a group or not. So, how to check whether it is a group or not? So, to check this, how do you prove it? Solution. Since it is a finite set, there are ways to prove. So, first one is that you can see that 1 into 1 is 1 only, it is closed. Minus 1 into minus 1, I into minus I, this is minus 1, it is plus 1, and then I into 1 is equal to I into minus 1 minus I also. I mean, you can see that all these elements are actually falling in the set itself. Therefore, it is closed. You take associative, 1 into minus 1 into I is equal to, so it is true with any element, minus 1 into I 1 into minus 1 into I is equal to minus 1 into I is equal to minus I. The same can be seen if you take minus 1 into I, it is minus I, and then now multiply 1 into minus 1 into I is equal to 1 into minus I is equal to minus I. True for every element. Therefore, you can say it is associative. And next, to find identity element. So, identity element. Identity element. Whenever you take, I mean, for all these identity element, for all these elements 1, minus 1, I, minus I, 1 is the element 1 is acting as an identity element. You can check it simply. It is like, you see, 1 into 1 is equal to 1. Of course, this is 1. This is the identity element. I can say that. So, and then minus 1 into 1 is equal to minus 1. This is identity element. And I into 1 is equal to I. Again, this is identity element. That's why it is giving just the other element only. Minus I into 1 is equal to minus I. This is identity element. It is true for every element. Therefore, this is the identity element. Next one is inverse element. So, what is the property to find the inverse element? For all A, there exists for all for every element in the for every element in the set, is there an element such that product of those two elements are equal to identity element? For example, 1 into 1 is equal to 1. This is identity element. That means 1 is having self inverse. 1 is having self inverse. And minus 1 is having, minus 1 is like 1. Again, minus 1 is self inverse, is having self inverse. Minus 1 is having self inverse. Okay, you take the other elements. Let's say that minus I. So, minus I into minus I, if you write, it is giving minus 1, but we need plus 1. Therefore, it must be minus 1 into I is equal to minus of minus 1, which is 1. Therefore, inverse of minus I is I, and I is minus 1, and inverse of I is minus 1, minus I. You should get output as 1. The same result you can obtain by using the table. Cayley table, you can write it. This is a finite set. Therefore, what you can do is that this is the operation multiplication. I can write it. There are 4 elements. I am listing all those elements: 1, minus 1, minus I, and plus I. Similarly, 1, minus 1, minus I, plus I. So, the same order. Now, I am trying to fill this table. Now, I am trying to fill this table. So, now multiply. 1 into 1 is 1. 1 into minus 1 is minus 1 into 1 is 1. Minus 1, and minus I into 1 is minus I. I into 1 is I. Next, move to the second column. 1 into minus 1 is minus 1. Minus 1 into minus 1 is 1. Minus I into minus 1 is I. I into minus 1 is minus I. And next, third column, 1 into minus I is minus I. Minus 1 into minus I is plus I. Minus I into minus I is 1. Oh, sorry, minus 1. And I into minus I is plus 1. Okay. And next, if you look at that, last one is 1 into I is equal to I. Minus 1 into I is equal to minus I. Minus I into plus I is equal to 1. And I into I is minus 1. Now, you look at this table, you can see easily, you can recognize that this table is exactly, this column and this columns are same. That happened with one only, one element. Therefore, 1 is identity element. Identity element. Now, to find inverse for each element, you see here, in each row where you are getting identity element, that is more important, where you are getting identity element in each row. I am focusing on the first row. I can see that the identity element, so 1 into 1 is identity element, 1 is happening with 1, therefore inverse of 1 is 1 only. Next, I am looking at the second row, because once the identity element exists in the one row, one place, and you cannot find anywhere else, therefore I am moving to the second row. To see the identity element in the second row, this is not, but this is. So therefore inverse of minus 1 is minus 1. Next, move to the third row. Third row is this minus I. I have to see that where is the identity element 1 staying. This is not, this is not, this is not, and here it is lying. Therefore that happened with I. Therefore inverse of minus I is I. And last row, if you look at this last row, if last row is this one, where the identity element is, the identity element is here, that is happening under this. Therefore inverse of I is minus I. So this is the other way to complete the, to verify the whether the given group, especially the given set, this is a finite set, therefore I am able to draw this table, then conclude it. It is not possible in infinite set, since it is a holding only finite sets, finite elements. This is a finite set holding finite elements, therefore I am able to verify this. And this is how we are doing. So you can check already, further examples, further you can verify R comma plus is a group, where R is set of real numbers, set of real numbers, set of real numbers. So you can say addition of two numbers, two real numbers is again a real number. Addition of three real numbers irrespective of a plus b plus c must be equal to, a plus b belongs to R, and a plus b plus c must be equal to a plus b plus c. Therefore associative closure, and for all a belongs to R, there exists a 0 belongs to R, such that 0 plus a is equal to a plus 0 is equal to a. Therefore 0 is the identity element, this is the identity element. And for all a belongs to R, there exists a b belongs to R, such that a plus b is equal to 0 is equal to b plus a, implies b is equal to minus a. Therefore this is a group. We have seen z comma plus is a group, implies R comma plus is also a group. In fact, you can say that a plus b is equal to b plus a, it's a commutative group, you can say. Similarly, q comma plus, this q is set of rational numbers. Is a group. Exercise. Q complement, set of irrationals. Is that a group with respect to addition? that is QC comma plus, is this a group? Is the question. You see here, so you pick any irrational numbers. I mean, those are of the form like irrational numbers, okay, or you can say that cannot be expressed in P by Q. So those numbers you take. So this is nicely satisfying closure property, associative property. But you see, when it comes to the identity element, that is 0, 0 doesn't belong to this, hence it fails. All other property is satisfying, therefore it is not a group. The other example is that exercise example r comma multiplication. You take r comma multiplication. Is this a group? A group. Is this a group? So the problem is that except 0 belongs to R, all other elements are holding inverse elements in R such that A into 1 by A is equal to 1. This is the unit element, or identity is the appropriate word to use. Identity element is the identity element. Suppose you take 1 into 1 is 1, 2 into 1 by 2, 3 into 1 by 3. Therefore, except 0, every other element is holding the inverse. But there is a problem with 0. Therefore, I can say that R minus 0 comma multiplication. Now it is a group. Of course, in fact, it is a commutative group. It is a commutative group. It is a commutative group. This is a commutative group. So you can take set of matrices. Set of matrices you can take. With respect to addition, you take set of all matrices of same size, m by m or n by n. You collect the set. Suppose you say that G is equal to A, B, C, D, such that A comma B comma C comma D belongs to R. This is your set, where R is set of real numbers. Real numbers. Now the question is G comma plus. Is that a group? Is that a group? Yes, of course, you can take addition of two matrices with real entries is again a closed. You add let's take let A1, B1, C1, D1 and A2, B2, C2, D2, A3, B3, C3, D3 are the three matrices you are taking, and order doesn't matter in which way you are adding, whether you are adding A1, B1, C1, D1 plus A2, B2, C2, D2, and that outcome you are adding A3, B3, C3, D3. This is actually equal to A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2. Similarly, you are adding with A3, B3, C3, D3. That implies A1 plus A2 plus A3, B1 plus B2 plus B3, C1 plus C2 plus C3, D1 plus D2 plus D3. Now you can take this equation as 1 and now you add A1, B1, C1, D1 plus A2, B2, C2, D2, A3, B3, C3, D3. If you add it, I mean this is A1, B1, C1, D1 plus A2, A3, B2, B3, C2, C3, D2, D3. And this is equal to A1 plus A2 plus A3, B1 plus B2 plus B3, C1 plus C2 plus C3, D1 plus D2 plus D3. Now, from 1 and 2 you can say that this is associative, both are same. Whether you are adding the matrices A plus B plus C or A plus B plus C, same it doesn't matter, order doesn't matter, whenever you are adding it is same result. Therefore, this is associative. Therefore, G comma plus is associative. Next, you have to see that whether there is any element that can hold the property of identity, that is capital A belongs to Z such that A plus some identity element I am writing as E is equal to E plus A is equal to A. So that is whenever you are taking A, B, C, D plus E, E1, E2, E3, E4 are the elements in capital E, that must be equal to A, B, C, D. And you see, if you the moment when you send, the addition is becoming subtraction the other end, and this is A, B, C, D minus A, B, C, D. The element wise subtraction is giving 0, 0, 0. If you compare the coefficients, E1 is 0, E2 is 0, E3 is 0, E4 is 0. Therefore, E is 0 matrix. Hence, it is holding because 0 is a real number. Therefore, it is NC. Therefore, G comma addition, G comma addition is holding identity element. The last one is that A, B, C, D belongs to Z. Is there B belongs to Z such that A plus B is equal to E, B plus A. Usually sometimes this need not to be same. There are cases where you can get right side addition, right side property may be satisfied, left side property may not be satisfied. But these are numbers and mostly it is straightforward numbers with the operations and then elements are well defined. There is no specific abstract form. Therefore, you can most of the cases is going to valid. And you see what does that mean? A, B, C, D, and I don't know, I am just calling that A1, B1, C1, D1 must be equal to 0, 0, 0, 0. We have seen that E is 0. So A1, B1, C1, D1 is equal to 0, 0, 0, 0 minus A, B, C, D. That implies A1 is like minus A, B1 is like minus B, C1 is like minus C, D1 is like minus D. Therefore, B is actually minus of A, B, C, D, which is actually A minus A. That is, for all A belongs to Z, there exists a minus A belongs to Z such that A plus of minus A is equal to E, and similarly this must be equal to minus A plus A also. Therefore, G comma plus is satisfying group property. So it is a group with respect to addition, the set of all matrices. Now you can check You can check exercise G is equal to the set A, B, C, D, where A comma B comma C comma D belongs to R, such that AD minus BC is not equal to 0 is G comma multiplication a group. It's multiplication, normal multiplication. Is that a group is the question. There you have to check, you have to pick A. A is A, B, A1, A2, B1, C1, D1, I'm sorry, where A is equal to A1, B1, C1, D1, and B is equal to A2, B2, C2, D2, and C is equal to A3, B3, C3, D3. All these are satisfying. Please remember the given, if those are the elements, according to this, A1, D1 minus B1, C1 is non-zero. That means A inverse exists. Those elements only were collecting in G. Here it is A2, B2, A2, D2 minus C2, B2 is not equal to 0. Therefore, B is also invertible. C is also A3, D3 minus C3, D3, B3, C2, C3, B3 is not equal to 0. That means these are the property. You know that whenever you multiply AB belongs to Z only, obviously, because product of two matrices, if determinant is not 0, then again resultant matrix determinant is also non-zero. Therefore, it must belongs to the same set G. Therefore, it is closed. And similarly, you take A into B into C is equal to A into B into C. Since A into B is need not to be equal to B into A, but A into B into C is equal to A into B into C. You can check it. It is satisfying the associative property. Associative property. It is satisfying. Therefore, it is satisfying second property also. What about the third property? Third property is inverse. That is, for all A belongs to, identity element, A belongs to Z is there. So, third property is identity property. For all A belongs to Z, is there an element E belongs to Z such that A into E is equal to E into A is equal to A. Yes, obviously E is like 1001 identity element, identity matrix. Yes, E is equal to 1001 is the identity matrix. So you can get it. It is usually we denote it by I. Therefore, it is satisfying. So next property is inverse. So since A belongs to Z, for all A belongs to Z, for all, actually it is not for one A, it is every A, holds the property that determinant of A is not equal to 0. That is, AD minus BC is not equal to 0. Therefore, inverse of A exists in G such that A into A inverse is equal to I, which is equal to A inverse into A. So, inverse of A is A, it is holding that property. So, you have to write it. So, this is how you are showing that G comma multiplication is a group where for all A belongs to Z, holds the property determinant of A is not equal to 0, not equal to 0. Further, we are only focusing on real numbers. That is, further A is equal to A, B, C, D with A comma B comma C comma D belongs to R. We also represent this notation with GL, actually GL2 comma R, that is general linear group, that is general linear group with A, B, C, D such that A, B, C, D belongs to R. Further, determinant of the matrix, that is nothing but AD minus BC. AD minus BC is not equal to 0. So it is a group. We have shown that. And last example, I want to take you one specific example. We will see few more examples in the next class, but one example I want to discuss is last example on groups. It is Q plus comma star with the star with, in which way star is defined, where star is defined with the operation star. Okay, last example is I want to give a last example on group theory, and further examples we will see in the next class. Okay, so example. So prove or disprove that Q plus comma star, where star is the binary operation defined by A star B is equal to AB by 5 is a group. Is a question, is a group. So first we will see where Q comma plus, note that Q comma plus is set of all positive rational numbers except 0. 0 is not part of that set of all positive. That means 0 is not there. Therefore, you pick any two numbers, that is A comma B belongs to Q plus, then AB belongs to Q plus, because product of two rational numbers, positive rational numbers, is again a rational number, positive rational number only. Therefore, AB belongs to Q plus, and since 5 is positive, 5 is also belongs to Q plus. Therefore, AB divided by 5 is also belonging to Q plus. Hence, Q plus comma star is why this is defined? It is A star B is equal to AB by 5 only. Therefore, Q comma star is closed. Next, you are moving to other property, that is associative property. What is that associative property? Whenever you pick A, B, C belongs to Q plus, you are checking A star B star C is equal to A star B star C. First, let's take A star B is equal to, according to the definition, AB by 5. And the moment when I take A star B star C is equal to AB by 5 star C is equal to, according to the definition, this is the first element, this is the second element. According to my definition, AB by 5, first element into second element divided by 5. This is ABC divided by 25. This is equation 1. Now I am taking the other one, that is B star C is equal to BC by 5. That is first element into second element divided by 5. Now I am taking A into B star C, which is equal to A star BC by 5. That is, according to the definition, it is the first element and second element divided by 5 divided by 5. That is ABC divided by 25. This is equation 2. From 1 and 2, you can conclude that ABC divided by 5 is equal to ABC divided by 5. Therefore, you can say that A star B star C is equal to A star B star C. Hence, it is proved it is associative. Next, to find the identity element. That is A star some element A star, I say that E is equal to E star A is equal to A. This property must be proved. This must be satisfied. Let me take A star E is equal to A. But A star E is equal to AE divided by 5 is equal to A. Okay. So that implies E is equal to A by 5A. Implies 1 by 5. Because A belongs to Q plus all positive rationals only. Therefore, 1 by A you can cancel on both sides. That is valid operation. Therefore, identity element is 1 by 5. For example, you take any element 2 into 1 by 5 is equal to, what is the output of it? I'm sorry, I think sorry. So yeah, if you take A into according to the definition, A into E by 5, this is E is equal to A divided by A into 5. This is equal to 5. As A belongs to Q plus, we can cancel numerator and denominator because A cannot be 0. So therefore you can cancel. E is like 5. Therefore, for all any element you pick it, for all A belongs to Q plus, 5 is the identity element. You can take 5, the same element is going to work for every element as an identity element. You take A is equal to 1, A is equal to 2, A is equal to 3, and for all those elements the 5 is the identity element. For example, if you have any doubt, you can check it. 2 element you are picking, 2 belongs to Q plus only. Therefore, 2 into E is equal to 2E by 5. But E is equal to 5. If you substitute 2 into 5 by 5, cancelling, it is 2. Therefore, it is satisfied. 2 into E is equal to 2 property is satisfied. Similarly, E star 2, actually it is star right here. E star 2 also similarly we can prove. E star 2 is equal to, again it is going to be 2 only. So both the ways we have shown, A into E is equal to, E into A is equal to A is valid whenever E is equal to 5 in this case. Next one is inverse element. For all A belongs to Q plus, is there a B belongs to Q plus? Is there a B belongs to Q plus such that A star B is equal to E is equal to B star A, but E is equal to 5. It is already known, the identity element. Therefore, A star B is equal to 5, but A star B, according to the definition, it is AB by 5. Therefore, AB by 5 is equal to 5, implies AB is equal to 25, implies B is equal to 25 by A. So therefore, for every element, for all A belongs to Q plus inverse, there exists an element B, there exists an element B such that A star B is equal to B star A is equal to identity element, but that is equal to 5. We have seen that. Therefore, B is equal to 25 by A. You can check this whether it is true or not. Suppose you take A star B, we should get E, that is 5, we should get it. Now I am substituting A star 25 by A is equal to, according to the definition, it is first element into second element divided by 5. A cancels because A belongs to Q plus. Therefore, 25 by 5 is equal to 5. That is the identity element. Identity element. Hence, you can find. Therefore, Q comma Q plus comma star is a group. Of course, in fact, you can show that A star B is equal to AB by 5. That is equal to BA by 5. That is equal to B star A. Therefore, Q plus comma star is a multiplicative group. Sorry, I'm sorry. Therefore, Q comma plus is a, therefore Q plus comma star, therefore Q plus comma star is a commutative group. Yeah, with this I'm stopping, and I can continue in the next class about a few more examples on groups, further examples on subgroups,